Um, Good morning, everyone. My name is Amir, and I'm R&D engineer with Quanser. Today, we are going to talk about our Quanser robotics package for education. Um, for those of you who are not familiar with the way that we provide our curriculum and other material for our education purposes, I'm gonna first talk about what we have for our robotics package for education. On your screen, you will see the folder that we have, and we provide curriculum, a full curriculum based on a Craig's and other famous textbooks in robotics. And we have user manual. As you can see, if I go to user manual, you have access to the full user manual of the 4DOS system. If I double click on that user manual, you will see more information on the 4DOS Miko from Kinova. And I'm going to tell you about the differences and the additional material that we provide. First of all, if you get the 4DOS Miko from Quanser, you will get a full curriculum, as I mentioned, but you can also control the robot using MATLAB Simulink. So that has a lot of advantages for educational purposes when students want to design their own controllers, talk about or learn about kinematics, inverse kinematics, Jacobian. The other difference or the other additional added material to this Kinova Miko is that we provide real-time control at 1 kilohertz. As you can see, if you get the robotics package from Quanser, this is the box or the case that you get with Miko, with all the cables and required material to mount the Miko on a desk or a table or wherever you're feeling comfortable with. As you see on your screen, we have it on our table, and you have access to all the information, all the requirements, what each port is for, and how you can mount it. And so in order for us to make this Kinova Miko robot real-time at 1 kilohertz, we had to add one fast serial card to the package. So if you purchase this Miko from Quanser, you get this card. You have to install, and we have a full installation procedure for you. And once you install this one, it basically changes the way it communicates normally with the PC, because the original controller from Kinova uses a USB connection and it runs at 100 hertz. But with this fast serial card, we could reach at 1 kilohertz. This has some advantages if you want to send force feedback as a haptic to a haptic device. Sending a 1 kilohertz makes a very good performance in terms of haptic feedback. So we have other setup procedures, how to install the card and how to run the PC. So if you want to get more information, you can take a look at the file later on. So other than the user manual, we have as I said, we have the full curriculum based on the famous textbooks. One of them is Craig's, and one of them is Spawn. And as you can see right now, we have developed 4 different labs from 4 different chapters of the book. We are working on the last lab, which is a more advanced laboratory for undergraduate students. So I'm gonna show you what material we have here for kinematics. One advantage of this Quanser package for education is that you not only get the robot, but also a full simulated robot in a virtual environment. So the students can go over the virtual robot, run their controller, and learn about the basics. And after they feel comfortable, they can go and run their controller on the actual device. So what I'm gonna do right now is that I'm gonna show you how the simulated robot looks like. So this is a MATLAB Simulink environment, and once you install Quark, you will see different options here. One of the added items to the Simulink is the Quark libraries. If you go to the libraries, you will notice that we provide a visualization toolbox. So this simulated robot is implemented fully with visualization toolbox of Quanser. If I compile this model, it takes about a few seconds to compile. Sometimes for the first time it might take a little bit longer. So now once it's compiled, I can run the controller. So you will see this is the simulated robot. Right now it's not talking to the actual robot, but you will see later on that we can directly connect this simulated robot to the actual robot, and they follow each other closely. So we can so you can see the simulated robot on the screen on the right side with some augmented reality. What we have here is all of the frames assigned to each link. So you can see the base frame, which is a fixed frame. The y-axis is towards the left, and by the way, is the same as the robot. And the x-axis is facing forward, and the z-axis is upward. So all these little red dots that you can see provide you a grid line to measure the distance of the end effector from the space. So right now you can see that the end effector is about 30 centimeter in the y direction, 0 in x, and about 50 or 60 centimeter towards the z. So if I take a look closely to the actual data from the simulation, you will see that it's about 30 centimeter in the x in the y direction. All right. So what students see is where the end effector of the robot would be using the actual kinematics. So what we provide, if you go to the text, if you go to the lab material, you will see that we have some background information for the students. They go through the pre-lab preparation, and they'll learn how they can assign the frames and what the DH parameter means for serial manipulators. And then we have all the required information for them to assign properly the frames to each link of the robot. And then once they go through the steps that we provide, they learn about the forward kinematics of the robot. And we have some questions or exercises for the students, so they can make sure so the prof makes sure that they understand the procedure. The students know how to assign the frames to the robot, and then know the DH parameters of the robot. And once they learn about these DH parameters, they go inside the simulated robot model here, and they implement the DH functions, and they implement the forward kinematics. So once they are done with the implementation, they can see where the end effector of the robot is located on the screen. So if they change, let's say, one of the joint angles, they know the effect of the first joint in this pose on the end effector is only on X and Y. They are asked to modify other joints, and they see how the virtual robot moves. They measure the distance from the of the end effector from the base, and they compare with the results they have from the exercise. So this is one of the examples of forward kinematics for this lab. So once they feel comfortable that they understand the forward kinematics and the equations and the background information, they stop this virtual model and they go to the actual robot implementation. So here I am going to run the first model, which is the forward kinematics. So this model is very similar to the one that they have for the virtual robot, except that it actually talks to the robot. So if the students go inside the block, they will see that inside the Miko IO block, they have Miko write, Miko read, and they can actually get all the information from the robot. The sensors that we have on the robot, they are encoders that gives us angles of joint angles. We can measure the speed of each joint. We have the current sensors. We have torque sensors at each joint, and we have temperature sensors. So what I'm gonna do right now, before going to the kinematics model, I'm gonna run a basic model that runs the robot, and we can see the measurements. Right now I'm running the model that talks to the robot. If I want, I can move the robot in different poses. What I'm going to show you here is that the joint angles, as you can see, we have all 6 joint angles. We have 4 joints for the robot, and we have 2 fingers. Each of them has 1 actuator, therefore we have 6 measurements. And if I move the robot, you will see the speed measurements for the robot as well. And then we have current measurements for the joint motors. So again, if I move this, the robot around, you will see all the current measurements, and everything is done at 1 kilohertz. And the torque measurements, for this one, I'm gonna ask my colleague to apply torques to the first joint, and you will see the effect on the measured torque. This is the first torque. The second one, again, the same thing. If you apply torques, you will see that you can measure it in real time at 1 kilohertz. The third one, the same. And the last and fourth one. Right now, we don't have torque measurements for the fingers. But if people require pressure sensing or torque sensing, they can apply their own pressure sensors, and we can try to integrate it with our Simulink program. So again, you can measure the temperatures as well. The temperatures of the joints change very slowly. Obviously, they don't jump. So you have to wait or work with the robot for a few hours to see a few degrees change in the motor temperature. The advantage of sensing the temperature is that you can use them to stop the controller if the motors get hot, and then send a notification to the user. So now that I'm running this forward kinematics, you will see the position of the end effector of the robot is at z equal to 73 centimeter and y equal to minus 30 centimeters, and x is 0. So x is forward, y is to the left, that's why the measured y is negative, and the measured z is 73 centimeter. Then the students are asked to do the same thing that they did with the virtual robot and send the robot into different poses. First of all, changing the first joint and see the effect on the x and y, and also the obviously the rotation matrix of the robot. So as you see, the z is not changed, but x and y are changed by changing the first joint. And then the same thing for other joints. So they are asked to change the other joint slowly. This is the way that I'm moving the robot, but you can apply different joint commands to move it slowly into different directions. With our Simulink diagrams, you have access to the limitation of the speed of the joint, so you can limit how fast the robot can move. So if you feel if you don't feel comfortable with the way that the robot is moving, if it's too fast, you can definitely slow it down if you need it. But the robot is actually very lightweight. It's 3.8 kilograms, and the payload is about 2 kilograms, so it won't hurt the students at all. The power requirement for the robot is about 100 watts maximum and 25 watts. And the maximum speed in the linear directions are 20 centimeters per second. But as I said, we have limitations here, and you can limit the rate that the robot is moving. So each joint has its own maximum speed. For the first 3 joints, the maximum speed is 54 degrees per second. For the last or the 4th joint is 110 degrees per second. For the finger, the measurements are not in degrees. And if the students want to open and close the jaw, they can apply different commands here to the last 2 joints. Right now I'm applying the same commands to the 2 fingers, that's why they're moving at the same time. So this is the first and one of the simplest lab that we have. As I said, we provide background information on DH parameters, how to assign the frames, but also we provide the functions for the students to apply directly to the robot to measure or to calculate the DH parameters and to calculate the matrices, and then the kinematics or forward kinematics of the robot. Alright, I close this model and go to the next lab. Very similar to what we had for kinematics, we have inverse kinematics. Again, we have controllers for this lab, and we have the source codes for or latex files for the lab material. So second lab, the topics that we cover is the concept of inverse position kinematics and how they can geometrically solve the inverse position kinematics of the robot, and whether or not there are solutions to the end effector pose, or we have multiple solutions. We discussed that as well. So we have some discussions on solvability and existence of solutions, how they can check if the solution exists or they have multiple solutions. And we have a whole section of discussion about geometric solution, how they can solve it geometrically, what the values are for each joint based on the given x, y, and z parameters. And again, for the instructor, we have solutions to the questions. And then when the students go to the in-lab exercise, they start working with the virtual robot again. So they apply different X, Y, Z commands to the robot, and they calculate the required joint angles. And then they apply these joint angles to the virtual robot and see the pose of the robot. And if everything works fine, if the robot is in a safe pose, they apply the same command to the actual robot in the experiment section. So right now, I'm going to load one of the models we have for inverse kinematics. First change the MATLAB path and then load my model. As I mentioned before, the virtual robot is based on Quanser's core visualization toolbox. And again, similar to what we had before, we have a simulated robot block here. We visualize it on the screen for the students, and this time we have an inverse position kinematics block diagram here. So if the students go inside the inverse block diagram, they can verify their derivation, and they can see if they could properly solve the inverse kinematics by themselves, and then apply this to the actual robot. By the way, because profs have access to the source codes, they can change whatever they want. We have seen some profs removing some of the lines and asking some of the students to come up with their own solution. We have seen profs that required attaching different tools to the robot and asking students to solve the inverse kinematics from the tool and from the tool frame to the base frame as opposed to the end effector frame. So here is the model. Again, I compile the model first. It should take about a minute to compile, and then once it's over, I can run the model. Alright, so now I connect to the target and run the model. Again, on your screen, you will see the robot having its pose, the virtual robot, and the applied command is 0 and 0 for x and y, and 0.7 or 70 centimeter for the z. And this is the pose of the robot. And for this model, the camera is rotated, but you have access to the keyboard. You can use the keyboard to rotate in different direction or move it into different direction if you require. And here the x axis is to the right, so you will see the x and y are 0 and the z is 70 centimeter apart. If the students want the robot go to other direction, to other poses, they can change the values of x and y. Let's say they want x go to 0.1 and y is 0 and z is 0.7. Again, the robot goes to that pose. If they want the robot to go to a different y point, they can change it as well. But what we have here, if they change it to, let's say, 7 and 7, the robot cannot reach that point, and it sends a command that cannot reach the requested point, meaning that the inverse kinematics doesn't have a solution, and they have to change the input command. So they can easily change the input command, and the robot moves to the command that they ask it to go. So again, the same thing. They will learn what the solutions are to the inverse kinematics. Here we have the two solutions achieved from the geometric calculations, and then if the inverse position kinematic solution is successful, we send a flag. If not, we send another flag and we show a message on the screen. And because the prof has access to the source, they can change whatever they need. They can change the, or they can stop the model if they want to be safer with the actual robot. This is what we have in the next section. So I close this simulated robot model. And trying to load the inverse. Yeah, it's already loaded. So again, this is very similar to what we had for the simulated robot. We have the Miko IO, and we have the inverse position kinematics, and the two solutions to that. To start with, I try to start the robot in a safe pose so that it won't move when I run it. And I think I forgot to compile the robot, the model. Once the model is compiled, we can connect to the target and it starts communicating with the robot. Forgot to set it to say pose, but that's okay. It will move and go to the pose that we sent to. So here, this is the pose of the robot, which is the same as what we had in the virtual robot. The Y and X are 0 and the Z is 0.7. So if the students want to change the X to 0.1, the robot goes 10 centimeters forward. And if they want to go minus 10 centimeters in the Y direction, they can easily change. And what they do is they go and look at the two solutions, and they see and figure out why the robot is picking up one solution based on the existing pose. And then if they send a command that is not safe, again they will see the command on the screen that there is no solution to the inverse kinematics, and the robot stops moving. So again, this is the same IPK that it was used, or inverse position kinematics, that was used for the virtual robot. Other labs that we have are Jacobian. We have Jacobian that has a discussion on what the Jacobian matrix is for the Fordov Miko, how they can calculate, how they can derive it. And if I go to the lab manual, you will see the meaning of Jacobian, how they can derive Jacobian, the different vectors of that, linear and angular part, and how the Jacobian is used to measure the torque based on the applied force to the end effector. So the two main usage of Jacobian metrics here. And then obviously they have pre-lab exercises. We ask them to derive different Jacobians at different poses for the robot. And then the same thing, they go and run the exercises for the simulated robot and then apply the same exercise for the actual robot. They can verify their derivation in the pre-lab, and then they can compare the differences between the simulation and experiment. So because of time constraint, I'm not going to the details of the models for these ones, but I can run the simulated I can run the simulated model for Jacobian, and you will get the idea of what we have. So again, we have the simulated robot, and then we visualize it using Quanser's visualization toolbox. What we have here is the Jacobian and inverse Jacobian, which also includes singularity avoidance. So if I compile and run this model, I can go and run the actual model. For some reason I'm getting error. I think the model is open. Alright. So if I compile this model, I can send the velocity commands to the end effector, and because of the inverse Jacobian, they're translated into the joint position command, and they apply to the robot and they move. And then in the other experiment we can apply different forces to the end effector. We can measure the torques of the joints. Two applications of Jacobian. So in the first one, I'm running the robot, sending to home position, and here I'm applying x dot command. So the robot should slowly move forward when I change the x dot, and the speed is about 1 centimeter per second. I can send it also back. Yes. I can apply in the y direction. So here it will move into the y direction and negative y direction, or positive y direction. Right now we have about 3 centimeters per second. And I can stop it. So the students learn how the x dot command or the commands in the Cartesian space, the velocity command Cartesian space, are translated into the joint space velocity commands and applied to the robot.